The most accurate way to find cosmological distances, distances to faraway galaxies and such, is to find standard candles. Standard candles are objects of known luminosity. If we can find known luminous objects in galaxies far and close, then we can measure the distances to these galaxies. We know how light acts. We know that we have something called the inverse square law of light. But before we can use the inverse square law of light, we need to measure distances to these standard candles closer to home in the Milky Way galaxy. So step one is to find standard candles nearby to Earth, measure distances to these standard candles using stellar parallax. Step 2, we find the standard candles in objects far away from Earth, and then we use inverse square law of light to measure distances to these objects. Using parallax is fairly straightforward. Because the Earth orbits the Sun and we move approximately 2 astronomical units every year, this change of position allows us to see stars from different angles. So as an example, in June, when I look at this star here, I would see the star in the background here. 6 months later, in December, the Earth is positioned on the other side. Now, from this angle, I look at the star and I see the star in the background here. So the star moved this much in that period of time. Now, this angle here is called the angle of parallax. And we can measure that. We can take pictures of the stars and we can see their back and forth motion against a background of faraway stars that don't move. And so there is a very simple formula that says the distance in light years is equal to 3.26 divided by the parallax angle. This parallax angle needs to be in seconds of arc. And so the distance to a star that shows a parallax angle of 1 second of arc is 3.26 light years. We call this 3.26 light years 1 parsecs. So we find the distances to standard candles by using parallax. Once we have their distance and their brightness, now we can use that information to find the luminosity of the object. One of the standard candles is called a Cepheid variable star. The Cepheid variable star changes its light every several days or several weeks. This variability tells us how luminous the star is incredibly. When we look at the graph of the period of variability, say in days, this is 3 days, 6 days, 10 days, and so on, versus how their luminosity changes, we can see this graph here. This is a straight line, so we can find distances to faraway objects by just knowing the period of the variability. Hubble himself found out that the Andromeda galaxy is a faraway object by looking at a Cepheid variable in the Andromeda galaxy right here. And this is how the star was changing its light over a period of several weeks. So by knowing the period of variability, he could find out how luminous this object is. By knowing how luminous it is, he could find out what the distance was. In our galaxy, the Space Telescope has found several Cepheid variables that we can use. This is the position of the Earth. This is the position of the Cepheid variables that are close by that we can use to measure distances to by using stellar parallax. Another object that is extremely useful for finding cosmological distances is supernova type 1a. Supernova type 1a is a white dwarf in a binary orbit with a red giant, and it goes supernova when the mass of the white dwarf increases beyond the Chandrasekhar limit, or 1.4 times the mass of the Sun. So we assume that the luminosity of all supernova type 1As to a certain limit are known values. And so if we know the luminosity, we can figure out what the distance is. This is an example of a supernova type 1A. Now, the supernova type 1A is a white dwarf in orbit around a red giant. And we can see the supernova from far, far away, billions of light years away. So it's one of the best ways to find distances to faraway places in the universe. Let's take a look at the inverse square law of light. We know that if something is twice as far, it'll be 4 times fainter. So if something is 5 times farther, it'd be 25 times fainter, and so on. So these are certain examples of how we can figure out the distance by using the inverse square law of light. We have 2 standard candles here, and they both belong to these BMW cars. Identical headlights, car number 2 and car number 1. One of them is 1 mile away, one of them is 4 miles away. Because car number 2 is 4 times farther than car number 1, it must be 16 times fainter. So if you find a BMW to be 16 times fainter than the closer one, then it must be 4 times farther. Here's another example. We have a BMW that is 3 miles away, so it's 3 times farther. It must be 9 times fainter. Or if the standard candle is 9 times fainter, it must be 3 times farther. Here is another example. Now, our astronomer here is observing object number 1, and she has measured the distance to this object to be 10 light years. Object number 2 is an identical object to object number 1, except it's 9 times fainter. And if it's 9 times fainter, then it must be 3 times farther. And this is basically your math. So we say, since object number 2 is 9 times fainter than object number 1, then object number 2 must be 3 times farther, because square root of 9 is equal to 3. And because the first object was 10 light years away, and the second object is 3 times farther, then it's 30 light years away.